so what I will talk about is the black hole stability problem, but like our previous speaker, I slightly changed what I will really talk about. And this already, I didn't change the title though, so it's slightly misleading. So this is already shown by the joint work part. So I talk about joint work with Peter Hintz, which means that I will be talking about the Kerr-de Sitter case, so the positive cosmological constant. I decided that I would really like to get to some technical, but not super technical things. And so I want to concentrate on that. So the first few slides will be quick because they're just recalling the background that come up so much. So the only thing is that because there's a sign with the cosmological constant, it matters, what your metric signature is, but I mean, you ignore it. So I just write plus, minus, minus, and then this is the signature, Ricci G plus lambda G 0 in four dimensions. Anyway, and then as usual, so Minkowski is lambda equals 0. De Sitter is lambda positive, anti-de Sitter will be lambda negative. And so I mostly talk about lambda positive corresponding to the current universe, as it's thought, for the time being. Anyway, and then just recall that this is a PDE because the Ricci curvature is derivatives, and it's nonlinear, and second derivatives. And so it will end up being a wave equation of a tensorial nonlinear type with some issues. And so the typical formulation for wave equations for many reasons, including a lot of historical reasons, is that you think of the initial data formulation on a space-like Cauchy surface. And for linear wave equations on global hyperbolic spaces, like Minkowski and de Sitter, everything is great for the linear equation. Solution is globally unique. For nonlinear equations, it's not automatic. And in both cases, though, you can ask, if you have Cauchy data and you perturb them a bit, how will the solution behave? I mean, in the nonlinear case, you also have to worry whether it exists. In particular, does it asymptote to what you perturbed? So this is an asymptotic stability, and maybe there's a family that would be an orbital version of that. All right, and so the issue that comes up immediately is the diffeomorphism invariance of Ricci. And so that means that if you have one solution, you have many. This sounds like all right if you want to solve equations, but it's, I mean, you just want a solution. But actually, because so some of the general theory for solving linear equations at the end of the day is duality arguments. And so this basically means, because it also applies to the adjoint operator of the linearization, that in fact it may not be easy to solve the equation at all, even though it's like, oh, I have a lot of solutions. So it's not quite a wave equation because of this, but it can be turned into one by imposing extra gauge conditions. And so one version is the harmonic or wave of, or the Turk gauge. So here you can put it in different ways. To fix a background metric, G0, and one requires that the identity map be a wave map. So basically, so a one-form wave equation. And so this is, okay, so that's what you want. So that's the extra condition you impose to get rid of this arbitrariness, corresponding to the diffeomorphism invariance. So that's important. But it's also important how you implement it. I mean, it's great to think of something that should make it unique, but for analysis, you have to implement it somehow. And so one way to implement this is using the second Bianchi identity. So the divergence of this trace reversal of Ricci is 0. And so the implementation would be to add the term, or subtract the term from the equation Ricci plus lambda G equals 0. This is my capital phi term. And this capital phi term is just the symmetric gradient of one form, this gauge one form, which I just wrote down. So the point is that once you do this, you do get a quasi-linear wave equation. And so this gets rid of the diffeomorphism invariance of the problem. So at least you have local existence and uniqueness. And okay, so you solved a different equation, which maybe analytically was well behaved. So you might be happy, but what about the original equation? So you get back to this because of second Bianchi. You just hit this nonlinear equation with the del G, 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 and the Ricci and the lambda G goes away. And so what remains from this phi G terms, I'm going through this because this will be of some importance later on, is this constraint propagation, so one-form wave operator, which I call box CP. So this is 2 del G, G, G del G star, being applied to this one-form epsilon. And so then the wave equation behavior then, I mean, this is a one-form wave equation. And when you solve Einstein, right, you satisfy constraint equations, so set up initial data, that will automatically give you vanishing Cauchy data for this one-form problem, so you conclude that the epsilon is identically 0. Right, and so this, I mean, a different term, but turns out essentially this is what enabled Choquet-Brouillard, so that's a harmonic gauge, so, or a wave gauge, so it's Minkowski space as the background, enabled for the local theory, enabled Choquet-Brouillard to show local well-posedness for the equation. Okay, so epsilon is 0, so you've solved the original equation you want to solve. All right, and so of course there's a long history of stability results, and so I mean probably the most influential in some ways the Minkowski space result of Christodoul and Kleinerman, which was later simplified by Lindblad and Rodnyansky. There were various other extensions and modifications like Bier and Zipser and Hintz and myself. But actually, De Sitter is even earlier due to Friedrich in the 80s. So this already shows that De Sitter in some way, so that's a positive cosmological constant, could be a bit better behaved. And that's actually the reason somehow you can think of the lambda equals 0, so the Minkowski in this case, as a very degenerate limit of positive lambda. And of course, it's a very interesting degenerate limit. It's a degenerate limit. So things are going to be typically better behaved analytically in lambda positive, or algebraically, everything is more complicated in lambda positive. So if you want to do algebra, then lambda equals 0 is your relative dream. If you want to do analysis, then lambda positive is your relative dream. Okay, so so what I actually talk about is the work with Peter Hintz on the stability of Kerr-de Sitter black holes, which are slowly rotating. And again, they've come up already somewhat in a number of talks. So let me just quickly recall what they look like, actually starting with the Schwarzschild-de Sitter. So, the whole family has a mass parameter m and an angular momentum parameter a. And so a equals 0 Schwarzschild-de Sitter, and then you can write down the metric explicitly. And the lambda equals 0 case is a Schwarzschild, and then the m equals 0. If you just format m equals 0 here, that gives you the De Sitter metric in a funny form in a coordinate patch, really. And right, so the basic thing that you do is that you stare at this metric, and then it all looks good, except that you're dividing by 0 in some places. This mu can vanish in some places, and so if m and lambda is positive, so remember lambda is the cosmological constant, then you have two positive roots of mu. If lambda is 0, then there's only one root 2m. And if m is equal to 0, then the only root is square root 3 over lambda. So in the degenerate scenarios that either lambda is 0 or m equals 0, one of them goes away. And in this form, the metric only makes sense, this is the Boyer-Lindquist version, in a certain region when R is between these roots. But they are coordinate singularities. You can the question is never whether you can make a good problem look bad. You can always do that. The question is the other way around, that can you make a bad problem look good? So so it's a coordinate singularity. So with an appropriate sort of change of coordinates, you can desingularize it. So basically change your time variable. And then these two roots, R minus and R plus, become the event horizon, the cosmological horizon, and your space-time beautifully continues beyond this. And so the time derivative, which is, dt and dt star are the same thing in this decomposition. So it's a killing vector field, and the whole metric is spherically symmetric. Okay, and then here's the picture. So in some sense, I think of the left-hand side as being the, so the philosophy is, right, analysis and sort of differential structure comes first. Second is things like metric structures, so like the causal structure and things like that. So somehow the left picture is what is the analysis picture. You have a spatial, I mean, this is not showing the spherical part. You have the spatial region, maybe a little bit extended beyond R minus and R plus, because maybe eventually you want to solve some nonlinear problem where these horizons will move and you can't just stop before them, so a little bit extended, and then cross this time interval going up to infinity. And if you want to look at the coarser geometry, that's the Penrose diagram that's on the right. All right, so I'm not going to say what the Kerr-de Sitter metric is, though it did come up in one of the talks, at least. So maybe in a couple of talks. So it has the same underlying manifold. So it's a metric on the same underlying manifold, and the time derivative is still a Killing vector field, and they are axisymmetric. But I'm not going to write them down. And I just want to recall which again has come up in a bunch of talks, the initial value problem for Einstein's equation. So for that, what you want to do is you have your initial hypersurface, your initial data Riemannian metric on the surface, so one lower dimensional thing, symmetric 2 cotensor, which satisfies the constraint equations, and then a Lorentzian metric solves this. Well, with my signature, if the pullback of the Lorentzian metric is negative, the Riemannian metric, and the other tensor is the second fundamental form. And so the result with Peter Hintz is the global nonlinear asymptotic stability of the Kerr-de Sitter family of small angular momentum on the region I showed. So let me just go back to this. So it's this region on the shown on this picture. Okay, and so here's the slightly informal version, because I'm not saying, for example, what kind of norms and things like that. So the theorem is just if you have smooth initial data on the initial surface, satisfying the constraint equations close to the data of Schwarzschild-de Sitter spacetime. So in particular, they can be, a Kerr-de Sitter that's slowly rotating in some high regularity Sobolev norm. Then there's a solution of Einstein's equation attaining these initial data and black hole parameters MA close to these initial ones, which was the Schwarzschild mass and Schwarzschild-de Sitter mass and 0, so that the solution decays exponentially at some rate independent of the initial data to this Kerr-de Sitter black hole with these parameters. So this is an orbital statement, right? Because you're not decaying to what you perturbed, because after all, you can't possibly, because Kerr-de Sitter itself solves the equation. So slightly perturbed Schwarzschild-de Sitter, you have Kerr-de Sitter, it just solves the equation, so you're not going to get Schwarzschild-de Sitter back. But you will decay to a nearby member of the Kerr-de Sitter family with the quantitative control of everything. So I already said the beginning, and then so the settling down is this is emission of gravitational waves, and of course LIGO. Generally one thinks of this as in the lambda equals 0 setting. Of course, lambda is in real life supposed to be extremely small. So for something like this, it doesn't really matter what lambda is. For the stability question, it does. Stability is an infinite time scale, right? So for the question, it's sort of a quantitative question. Is lambda positive? Is lambda equals 0? Or is lambda negative? As soon as it's positive, it sort of changes the overall behavior quite significantly. The particular value doesn't matter. All right, and so as I said, I want to not really talk about lambda equals 0. So it's analytically significantly more difficult problem, basically because it's a degenerate limit. And so we're not quite there yet, but a lot of progress has been made recently on the lambda equals 0 problem. So due to, most recently, to Dafermus, Holzheiger, Rodnyansky, and Taylor, and we heard a talk about this, which is a finite codimension Schwarzschild stability result, and there were earlier restricted results of Kleinerman and Schaftel. There's a whole bunch of linearized results. So for example, Dafermus, Holzheiger, Rodnyansky, Anderson, Begda, Blue, and Ma, and Hintz, Haefner, and myself. And there's a whole bunch of other works related to these that are various ingredients. So there are many things that happen in the black hole stability problem. And you know, it's not like any one ingredient by itself does the job. So you really have to do all of them at the same time. And so some of these will come up in a little bit. Questions so far? Yes?
How does this alpha relate, the estimate that you had? How does this relate to the lambda constant?
Oh, so it will come from the so the main thing it comes from is quasi-normal modes. So so it will relate to the because of so we can scaling invariance of the equation. It will relate to lambda quite explicitly.
Okay.
Yeah. Mm-hmm. I mean, in some ways, right? What you think about in terms of a real life stability, I mean, a real life waveform is a particular time scale. So you never really are an infinite time scale, but the stability problem directly says what happens on an infinite time scale. So, all right. So what I want to spend most of the time on. So I hope they didn't rush too much until this point to get to this, is I want to go through in somewhat more detail the idea of proofs, because I somewhat feel that I never get to these sort of things in talks. So, okay, so, and that's also a reason why I decided to concentrate on positive lambda, so that I can do justice to at least one thing. So this is, so the way we approach this problem is using a nonlinear, I mean a non-elliptic linear global analysis with finite coefficient, finite Sobolev regularity coefficient. But so I will comment on this in a moment. So it's global. So it's global on the region we are working on. The nonlinearity is dealt with a very simple global Nash-Moser iteration. And the main reason at the end of the day is to do this Nash-Moser as opposed to something else is simpler, is the trapping. But realistically, once you get to do the Nash-Moser, your life is so much simpler. It's hard to stop doing it because you have to be much less optimal in all your estimates. So you're really very happy. All right. So so this is the overall picture. You want a linear, but in this case, a non-elliptic. And I want to emphasize non-elliptic because it's global. So hyperbolic does not do justice to the problem. There's something happening at infinity that's very badly described by saying it's a hyperbolic problem. If you go to finite times, sure. But you go to infinite times, this is like a completely inadequate description. There's more to the problem. So it's two parts. And so what's needed for this to go through, and I will discuss this all in more detail, is that certain dynamical assumptions are satisfied, which is, oops, I'm losing my microphone, which is basically that the only trappings, I talk a bit about this, is normal hyperbolic trapping with an appropriate subprinciple symbol condition. And the other thing is that there are no exponentially growing modes with a precise condition on the non-decaying one. So non-decaying really, for a nonlinear problem, is really as bad as growing, essentially, unless you are really lucky. So you really should just think of it as really just as bad. And so these modes are, so these quasi-normal modes or resonances. These are just non-trivial solutions of the linearized equation, linearized at the thing you are perturbing, which are just some exponential oscillating. I mean oscillating, but the imaginary part of the oscillation is non-zero necessarily, times a function of the spatial variables. Right? So it's a typical quasi-normal mode solution. So the thing is that there's a general analytic framework which requires two inputs. One is checking some dynamical assumptions, and two is checking something about these quasi-normal modes. All right, so I want to discuss the analytic aspects first, and then face various geometric extra complications. So Okay, the way we approach this problem is to face all of our issues from the start by working globally. So we solve all of our linear and nonlinear problems globally on this region omega. So this is the picture I had before. Yeah, so on this omega, this is where everything is solved right away. So all the arguments take place on omega. Now the nonlinear aspects can be reduced to a precise understanding of the underlying linear problems. I think this already came up, or also came up in a number of talks. By linearization iteration, of course, if we were doing something elliptic, this would be really easy. We are doing something that's non-elliptic, so you have to do something more sophisticated, like Newton or Nash-Moser. So this requires a finite coefficient, finite regularity coefficient linear theory. But anyway, so these nonlinear aspects are really not serious if you understand the linear problem. And then, so I mentioned this finite regularity of the coefficient basically requires slightly more care in the argument, but almost the same as in the smooth coefficient setting. So again, I will not really discuss this. A sharp version was actually worked out in Peter Hintz's thesis. There's a predecessor. So this is for this global problem. For just the local behavior, this was done by actually Beals and Reed in the 80s. And if one uses Nash-Moser, one can be much more forgiving. I mean, losing 23 derivatives, who cares? So anyway, so if one uses Nash-Moser, then you really don't have to be all that careful, and everything becomes much simpler. So again, I'm not really going to discuss this. But I'm considering the real core of things, which is the smooth coefficient linear analysis. Okay, so again, what I'm trying to do is to solve an equation. And so for this, I want to think of my operator. This is a linear operator. Right? This is my linearized, say, gauge-fixed Einstein or something like that. So why, or maybe it's a straight wave, simple scalar wave equation. Anyway, so I want to, the setup has to be, I mean, what do you mean that you invert, solve an equation? It's really amounts to inverting an operator. So you have some continuous linear map between two spaces. And so you have a lot of freedom. Like in elliptic theory, you always feel that why bother about functional analysis because your spaces don't matter. That's basically elliptic regularity. But when you get to more interesting problems, you have to bother a little bit. So you have a lot of freedom, but you have to be able to fix something, and it's good to confront this right at the outset. So basically, we are really confronting all the problems from the outset. And for us, these spaces will just be exponentially weighted in T star, this modified time variable, quote unquote. So exponentially weighted Sobolev spaces. Just these two indices. That's again something that's, life is much simpler in these sort of things for Kerr-de Sitter than Kerr, which is one reason I really want to talk about this. And I should say that with some extra information, the initial and final Cauchy surfaces. So there's a nice way of imposing initial values and not imposing final values by working on Sobolev spaces or distributional spaces, which are supported at, I mean, the technical term is supported at one end and extendable at the other. Anyway, these are, so I'm going to ignore that. This, of course, is very important because that's what gives you that you're solving the equation forward or backward, which is what you, for solvability, you really want the surjectivity statement, which is really coming from the adjoint operator. So you're really solving the adjoint backwards. Anyway, solvability is a surjectivity statement. And so the almost surjective version is the semi-Fredholm estimate. So where you estimate some function v by the adjoint of the operator applied to it modulo a relatively compact error. So you have to do this in the dual spaces of where you're hoping to solve the equation. So I was originally, I'm hoping to solve my equation with the right-hand side in y and the solution in x. So the two are reversed for the adjoint problem. And so concretely for us then, I mean, I said what the what the spaces are. I see I was inconsistent on my notation, but there I put an H or just the indices on the norms. But anyway, so you have to do basically a Sobolev estimate, which is, so M is the order of of P, so it's 2 for us, differential operator. And so basically just both X and Y are Sobolev spaces, except this X is a slightly more clever space. And so it's sort of like a graph space, which of course is easy to write down. It's a Hilbert space, but more importantly, it's a reasonable space. So you have a density of C infinity in it, et cetera, which come from basically just a little bit of work checking that this is not too much of an extra condition over what you a priori know. I mean, a priori you lose M derivatives, and this Y is only losing M minus 1. So that's why you have to think a little bit about it, but it's not bad. Anyway, but this estimate, the estimate is just straight Sobolev space estimate. That will automatically imply this. So the key thing is to get the Sobolev space estimate. And so that's proved in a 2-step process. So first, you prove an estimate where, so notice that the statement here, I wrote down the form of the estimate and then said that the inclusion of X star into this compact, this term, Z, the error term on the right-hand side, has to be compact. So what this means on the Sobolev space is that you have to gain both differentiability and decay. And so usual way this sort of thing is proved is in a 2-step process. So first you gain differentiability, and then you gain decay. So the differentiability, so the point is that on the right-hand side, my error term did not improve in terms of decay. So all of my decays are minus L. So remember, I'm trying to get the solution in an L-weighted space. That means dually, everything is in a minus L space. And so, okay, so this is not going to finish things because I don't have a relatively compact error. So this part uses microlocal analysis, which I suppose is the elephant in the room that I'm not going to talk about. But it's a very straightforward microlocal analysis. So it's really, really very, very nice and pretty. And it will be as beautiful as it is. It will be a bit of a distraction from everything else I want to say. So I'm not going to discuss this. But it's like, at this point, so off-the-shelf microlocal analysis, and nothing, you don't have to reinvent the wheel. So, and I want to point out, in principle, all of the ingredients of this microlocal analysis part, are unchanged for the full sub-extremal range, provided that you check the dynamical hypotheses. And so this is actually being written up currently with my postdoc, Oliver Lindberg-Petersen. So basic write-up is done, but we have, there's actual computation in this, unfortunately, unlike in the microlocal analysis part, where there's no, everything is, all the computation is super simple. Here, there's an actual not so simple computation to do. And as Rita already indicated in the talk, her talk, Kerr-de Sitter is, anytime you have to do any computation, it's, can be a headache. And you better check it many, many, many times. So we are doing that. All right, so step 2 is to prove an estimate for a model operator. So this step 2 is where you want to gain decay. And so there you want to prove an estimate for a model operator at infinity. So, you are trying to prove stability. So this is going to be a Kerr-de Sitter space that you are asymptoting to. And so the estimate is just, so this is like a no error term estimate on the right-hand side, but this is just for the stationary model that you are asymptotic to. And then you simply apply this, let me just go back to this, you just you apply this estimate for the error term on the right-hand side, and more precisely to a cutoff version of that I didn't write down. And anyway, so once you do this, you very easily get the semi-Fredholm estimate you wanted. Okay, now, so I have to comment, of course, it's semi-Fredholm, it's not actually surge activity, etc., but I'll comment on it in a moment. But so let's discuss a little bit where this estimate for P0 comes from. Stationary, so of course you do the thing that you want to do. You do a Fourier transform to obtain a family of this, the Fourier conjugate family in the Fourier dual variable of minus T star. And so then you have a family of operators, actually an analytic family. So analytic Fredholm theory is automatically applicable, corresponding to the step 1 estimate. I mean, so this was, step 1 was global in the space-time, but in particular, I mean, it does something in the limit. What it does in the limit is saying that you will have a Fredholm theory for this Fourier transformed operator as well. It's easy, strictly easier. All right, so so you have an analytic Fredholm theory. Now, which of course doesn't quite give you invertibility. It gives you that, I mean, you will automatically know that this P0 hat sigma is invertible for sigma large in appropriate places. So it's going to give you a meromorphic inverse. So there's going to be some poles, which are the resonances or quasi-normal modes. Now, there's a small wrinkle, actually, for if you really want to think about the full sub-extremal range of Kerr-de Sitter. For large angular momentum, so the ideal world for doing a Fredholm theory is like the sort of thing I said, where you lose one derivative and you don't have to worry about extra things. Losing one derivative will happen because, even in short Kerr-de Sitter, even for this Fourier transform problem, we are going beyond the horizons. And so we have basically a hyperbolic problem right beyond the horizon. So there will be a wave equation behavior. But you don't want to lose more, so you really don't want to have to work on a trapping version, etc. So it turns out that with a better choice of dt star, so the killing vector field you use in the decomposition, you actually can make this work nicely for even large A, so in the sub-extremal range. All right, so having done that, and again, this is due to work with Lindblad-Petersen. So having done this, the question is invertibility. So so whether this has a non-trivial null space, and this is how resonances enter. And so the net result will be, so as I said, this is analytic Fredholm theories have a meromorphic inverse, so you get a discrete set of resonances. And again, they actually cannot accumulate in some upper half plane, which corresponds to, the bottom of the upper half plane corresponds to the decaying space, so decaying resonances. So anyway, the upshot is that you have some discrete, so actually it's finite if you're slightly above. So as long as you avoid so choosing a weighted space amounts to choosing a horizontal line. You have finitely many resonances to avoid. As long as you avoid these, you are set. You get the estimate that you want, and you have your semi-Fredholm theory. Okay. In combination, if you are so I had all this bunch of resonances. If you're above all of them, so it's a weak weight, so growing, then you get, in fact, it's not just semi-Fredholm, but you're going to get the full surjectivity and solvability result. And then as you make the decay smaller, so one way to think about it is you're doing a contour deformation. You are crossing resonances, so you're picking up the quasi-normal modes. So what you get is solvability in a decaying space up to, so the solution will include a finite number of terms given by, potentially growing for linear problems, you say, who cares, potentially growing quasi-normal modes. And of course, for the nonlinear problems, the growing quasi-normal modes would be an issue, but we have to worry about this later. And so this is the extent of the analytic discussion before I get to the geometry part. Again, so this works again in full generality, modulo this mode analysis. So recently there's been some very interesting work of Casas and Teixeira da Costa. And so we're very interested to see, including this Kerr-de Sitter setting, we're very interested to see whether this can be done in the full sub-extremal range. Okay, so for the last part of the talk, I want to talk a little bit about the geometry. And so what I talked about before is applicable to wave equations. So like the gauge-fixed Einstein. If you think of it as linear, and then if you're nonlinear, then then you would have to have this quasi-normal mode assumption put in that there are no growing ones, and even the non-decaying one should have some structure. All right, but unfortunately, in this harmonic wave, the third gauge, while the dynamical assumptions are all satisfied, everything I told you is all satisfied, there are growing modes. Of course, who cares about this for linear, but for nonlinear you care. Even though there are only finite domain resonances above this line, and so so that's a key issue, right? And so some of these, I mean, it's not quite growing, but non-decaying, which I keep claiming for nonlinear is just as bad, almost just as bad, is just the Kerr-de Sitter family itself. So just perturb the Kerr-de Sitter family, look at the linearized level. This gives rise to resonances. But these correspond to nonlinear solutions, so it cannot possibly be a big deal. Just have to put it right. OK, so then one might expect the other non-decaying, so including growing modes, to come from the diffeomorphism invariance, so from gauge issues. That maybe this gauge is not quite the right gauge. But this is actually not true. I mean, it's not just that it's hard to, it's just not true. There are growing modes that are not like that. And this is explicit for de Sitter. And this is completely analogous, by the way, to computations done by Graham and Lee in the Riemannian setting for asymptotically hyperbolic space. It's actually exactly the same computation. All right. So there you want Poincaré-Einstein metrics. But the key point, so this is not just we can't show that these don't exist. They exist, period. But the key point is that we can arrange for partial success. So we can modify. So remember, we had our gauge condition, which was that this one form epsilon is 0, and we imposed it. So that was one choice. That was not the only choice we made. We made the second choice. The second choice is to implement this by inserting into the Einstein equation with the symmetric gradient put in front of it. That was another choice, independent choice. So you can get to a partial success by modifying it by a zeroth order term. So I'm adding to this. So I'm just taking the, say, the symmetric gradient with respect to the background metric, which I'm calling G0 here for some reason, with a different G, but anyway. So there it is. And I'm adding to it some zeroth order terms. So it's a first order derivative and then with zeroth order terms. And and some of the key part in the work with Peter Hintz was to show that for suitable choices of these parameters, this gamma 1 and gamma 2 that we are adding, which we actually made very large to make the analysis easy, because asymptotic analysis tends to be easier. This preserves all the dynamical requirements. And while the gauge Einstein equation will still have growing modes, it will have a new feature that the one-form operator, this constant propagation operator that's induced by it, so the effect, right, is you replace the symmetric gradient by this perturbed symmetric gradient, has no non-decaying mode. So all its mode solutions are decaying. And again, the one-form operator is just like the tensor operator or the scalar operator in terms of the analytic theory is exactly the same. The only issue you face in all of these things is what are the quasi-normal modes doing. All right, but so this one, once you modify this, there are no, so using this large parameters gamma, you can show that there are no non-decaying modes. And philosophically, there's really no reason to expect that this harmonic, the third gauge is well-behaved in any way, except in the high differential order sense, which is relevant for local theory. So I think in other like Riemannian problems or Ricci flow, et cetera, there are also similar things happening where they modify things by low order terms because in the long time limit, they become just as relevant. All right, so this is really constraint damping, or actually originally in the first paper where it came in, it was called stable constraint propagation, which is somehow unaware of this. We happen to call it exactly the same, luckily. Anyway, and this was used in the numerical literature, relative literature by Pretorius and others, following the work of Gundlach and others, to damp the numerical errors in this gauge one form epsilon. And so basically we show why such things work for this global problem. And the reason why it's useful is that previously we had this modified Einstein equation that's just a crazy equation. Okay, it's fine for local theory, but it's really a crazy equation. It's nothing to do with Einstein, it seems. If you really think globally, as I'm telling you that you really should. But once you have this extra information that this one-form operator has no non-decaying mode solutions, all of the mode solutions for the gauge-fixed Einstein, the gauge-fixed Einstein's equation are automatically mode solutions for just linearized Einstein, so without any gauge things put in. So that means that the a priori crazy mode solution we had that had nothing to do with anything, it just comes from implementing Einstein in a particular way to make it into a wave equation, actually turned into something geometric, namely related to Einstein. So and this constraint damping is crucial for this. This is basically second Bianchi. So all right, so of course, growing modes are still a disaster for nonlinear equations, so it's all great that you have a solution of Einstein. So you have to have a statement that they're all coming from diffeomorphism, linearized diffeomorphism issues that, as we hoped before, but which is not true before. I mean, one can hope things, but doesn't mean they're going to be true. So they weren't true. Now they're true because we did this constraint damping. And so this is this ungauged Einstein mode stability, which has been discussed in the physics literature for a long time, goes back to Reggie Wheeler, Zarelli, and others. And then the invariant form that we use, that's really close to exactly what we needed due to Ishibashi, Kodama, and Seto. And so let me just finish by saying that, so if you didn't have the zero modes corresponding to the quasi-normal modes corresponding to the Kerr-de Sitter family, so let's go to UMS star, because it's modified. So it's true for de Sitter, for example. Then there's a very simple way of showing global stability, namely, instead of this term I added, which was this modified symmetric gradient applied to epsilon, I add an extra or subtract an extra term in the argument of the symmetric gradient, theta, which is supposed to lie so it's unknown, so you're solving for it as well. It's supposed to lie in a finite dimensional space of basically things coming from the quasi-normal modes, which are, because of this ungauged Einstein mode stability, coming from symmetric gradients. Maybe I'm not going to go into it, but it basically comes down to the reason why you can do this is because you can solve the linearized equation without this theta, right? So if I don't have this theta term now in my phi, all that happens is I solve linearized Einstein and get this mode expansion, and finitely many modes are more growing than what I wanted. I'm going to just put them on the right-hand side. I'm going to put them into theta. This is exactly how this is set up. So there's really no magic here once you've done it. And it's not hard at this point to deal with the full Kerr-de Sitter family, by just adding another term. So it just requires slightly more messing. But the upshot is that in our solution method, both the black hole parameter beta b and this gauge variable theta are found along with the metric we are solving for on G in the nonlinear iteration. And so this gives the nonlinear stability of Kerr-de Sitter for small a. The small a comes in mostly, most strongly because of the quasi-normal mode issues that I mentioned. So I have no idea, what one can do for large A at this point. The other things, the dynamical things, actually even for the tensorial waves, work of Peter Hintz, relying on earlier observations of Mark, show that in fact even at the trapping, the tensorial waves are so the subprincipal term matters there, and even that is well behaved. So I think I managed to get through this more or less in time. So thank you very much. I hope I wasn't too fast.